Stanford University.
All right, guys, welcome to CS 193P Lecture 10. Hard to believe we're already on the 10th, but there we are. So we're going to talk today about performance. We spent some time on Tuesday. Chris told us all about getting our data, how we'd store it in files, get it out of the files, get it off the network, and all that kind of thing. He also showed a demo at the end of pulling some data off Flickr and putting it into a table view. And I don't know if you guys remember, if you saw it, while he was scrolling through that, the scrolling was just incredibly jerky, because while he was pulling it down, he was actually blocking the table view self-row at index path method from returning until the data came in off the network. And the user interface can't update until you return from that. So we're going to talk about some ways today that you can address that, and actually a whole bunch of other performance issues too. Before we get into that, just a couple of announcements. The assignment for this week is posted now, Paparazzi 2. It's due next Wednesday. I'm sure that's no surprise, given this point in the course. We left a little bit of this kind of up to you guys to read some documentation, just a little bit more than we had in some of the other ones. There's still a bunch of information in the run-through, and it gives you pointers to the right documentation to read. And we talked a little bit about, Chris pointed a couple of classes that are going to be useful on Tuesday. He talked about that. But for the most part, everything you need to know to find the right information is in the walkthrough. You may have to read a little bit more of the docs than you had to in the past. But all the information is available, and of course you can ask questions if you have any. This Friday, tomorrow, we actually do have a Friday section this week. It's in Building 260, Room 113. That's going to be, we'll have a visitor actually come and talk from Yelp. So that should be actually pretty exciting. I hope you can make it and check out, see what he has to say. Should be pretty good. Before we get into any of the performance things we're going to talk about today, I just want to briefly cover one other thing you'll need for your homework assignment this week. We had a very brief introduction to core data, but core data is actually going to be a pretty integral part of the assignment for this week. If you haven't checked it out yet, basically you're going to be storing all of your picture information in a core data database. And I guess Al showed a little bit at the end of the class how you'd set up some of those core data, the model objects in Xcode. The other piece that you need to know about that is once you've got your core data database set up and you've got data in the database, how do you get it out and get it into your table view? And there's a class in, I guess, Foundation? I'm actually not sure which. In core data.h? Well, NSFetchResultsController.h actually is the header that defines this. NSFetchResultsController, it's basically, it's a predefined controller object that you can utilize. It kind of sits between core data and the core data database and your own controller. So it's a little odd. It adds an extra controller layer inside your model view controller paradigm. But it basically sits there and is an intermediate between the core data database and your controller. And it provides a lot of really useful functionality when the thing you're trying to do is populate a table view from a core data database. So it basically interacts with the core data database on your behalf, as I said. And it defines quite a few methods that are interesting, but the first one that you'll find of a lot of use is object at index path. And this will return the object in the core database that you'll want to be displaying for a particular index path in a table view. And then the second interesting thing on NSFetchResultsController itself is the sections method, which returns you an NS array of section objects. And those are objects that respond to another protocol defined by NSFetchResultsController in the same header. And that's the NSFetchResultsSectionInfo protocol. And this protocol defines a few methods that are interesting for answering some of the questions that UI Table View is going to ask of its data source. And so those questions are, number of rows in table view, number of rows in section, and self-row at index path. So there's a method that you can call, obviously, right there, sections, which returns the NS array. And the count of items in that array is basically the answer to number of sections in table view. Then there's NSFetchResultsSectionInfo. You can ask it how many rows there are in it. Basically, you can ask it for how many items it has. And that'll be the answer to number of rows in section. And self-row at index path, you can basically use that index path and pass it to object at index path on the fetched results controller to get the object from the core data database that should be displayed in this particular row. So it's basically, it's pretty natural. I mean, it was designed specifically for use with UI table view. So if you just take a look at the header, it's pretty obvious, and there's comments that point you towards it as well, and also good documentation. Which methods match with which which methods match to which methods in your data source and delegate protocols. And it can really simplify a lot of the interaction between core data and UI table view. It's a great class, and it's super useful when you're trying to do these kinds of things. So before you go off and try and do a lot of work trying to figure out how to interact with the core database yourself, take a look at this, because it's going to save you a lot of time. All right, so that's just a little preview for what you're going to be doing this week. As far as today's lecture is concerned, as I mentioned, we're going to be talking about memory usage. This is a very important thing for performance on the iPhone. We'll talk about leaks and how they happen, how you can find them, some of the tools that we have available for locating them. Auto-release. We've talked a lot about auto-release and memory management in general. And so hopefully everyone's got a good feel for retain counts and when they're incremented, when they're decremented, what auto-release does. There's some side effects that you have to be careful for when you're using it. So we'll talk about some of those today. And finally, system warnings is the last memory usage thing we'll talk about. There's no... so the virtual memory on the iPhone will not allow the phone to have more. So it behaves as a. Yeah, let me try that one again. Virtual memory on the iPhone exists, but only for paging things in and out that are static on disk. So if you have a file on disk and it's mapped into memory, it won't necessarily read the entire file right away. It'll read it in as the data is needed, and it can page it back out if that memory is needed for something else. But what's not there is the dynamic memory swapping. So if you have some dynamic memory that you've allocated in your heap, you've allocated a bunch of NS strings in memory, those will never get paged out to disk, which is pretty different from what happens on Mac OS X or most other modern operating systems. The thrash on the flash is just a little too much, so that's not enabled. The thing that replaces that basically is system warnings, memory warnings. And you basically end up having to deal with this case on your own in your application, and we'll talk about that. And then we're going to end up with some talk about concurrency, threading, putting things on background threads, doing things, multiple things simultaneously without blocking your main thread so that user interaction can continue while you're doing your processing, and some additional tips and tricks at the end. All right, so before we actually get into this overview, anyone have any questions about anything? Hopefully everyone got the assignment in yesterday. We're good to go? All right, so let's talk about a bit about performance. As I started to mention, the iPhone has a very limited amount of memory. Some of the newer models that are shipping now have a bit more memory than the original, but in every case, it's much more constrained than on desktop systems. We're not talking about multiple gigabytes of RAM. We're talking about hundreds of megabytes. So the amount of room that you have to play with in your memory is pretty limited by comparison. So you also have slow or sometimes available, sometimes not network resources. It's a small computer that's taken with you all over the place. Your availability of networks changes pretty often, and so you often have to deal with you're downloading data, no problem at all, and then all of a sudden the network's gone. It's a situation that doesn't exist so much on the desktop, so you want to be careful of that when doing programming on the iPhone. And also the hardware is much less powerful. We're not, again, talking about these incredibly powerful graphics processors and CPUs that we have on desktop systems. The constraints we have on the mobile platform are quite a bit different. So with less powerful hardware comes more consideration towards performance. So you want to write your code with a lot of these considerations in mind, and use a lot of the performance tools that actually ship as part of the Xcode toolchain to optimize your memory usage and limit the amount of memory that you're wasting. And things that they're always important anytime you're writing code, but on embedded platforms like this, even though it's a full computer and feels like a very powerful operating system, and it is, you still have more constraints than you do on other traditional computing devices. All right, so we're going to start out talking about memory usage. Some of the things that we want to look for when we're dealing with memory on the iPhone, we want to load things lazily. Since we have such a limited amount of memory available, you don't want to, at launch time when your application starts up, just read in everything that you're ever going to need off your disk and try and keep it all in memory for the entire lifetime of your application. Not only is that going to hurt your performance with launch times, it'll take a long time to start your application, but you may not even be able to fit it all in memory. And we'll talk a little bit about what happens in that case in a minute, but basically, if you try and load too much too fast and don't take care of that, this operating system is actually just going to kill your application. So you may not even finish launching, and you really don't want that. So you want to load things lazily. You don't want to leak for the exact same reasons. We talked a lot about this with retain counts. If you increment your retain count too many times and don't release enough, and then throw away your reference to that object, no one's ever going to release it. It'll sit in memory forever until your application quits. So you want to be very careful about leaks. And happily, though, leaks are actually quite easy to detect with some of the tools that are available on the iPhone. So we'll see that in a little bit, but it's actually one of the more easy problems to solve. And you also want to watch your auto-release footprint. I kind of mentioned that we're going to talk about this, and we'll get into more depth in a minute. But you can basically, if you're using auto-release pools and you're not careful about it, you can end up ballooning the amount of temporary memory that you're using. Even though you've auto-released all your objects and all your retain counts are evened out, the auto-released objects don't actually go away until that auto-release pool is popped. So if you're doing something in a tight loop and generating a lot of objects, you may actually be building up a lot of temporary memory more than you really think. So we'll talk about that and see how you can actually find that using some of the built-in tools. And finally, we'll talk about memory reuse. This is a concept that we introduced a little bit when we talked about table views. Table view actually has this DQ reusable cell with identifier method, which lets you reuse table view cells. As we talked about it a little bit. As the user scrolls the table view, cells go off the top, they get pulled out and put into the reuse queue. You can DQ them and fill in new data and reuse them for the new things as the user scrolls new content in on the bottom. The idea is just to minimize the amount of churn with allocating and releasing objects, and we'll talk about that a little bit too. And then finally, if all else fails and you think you've done all these things right, but you're using a lot of memory, or maybe you've had a leak and just didn't notice it, the last thing that's going to happen is system memory warnings. These should really be your last resort. To the best of your ability, you should minimize the amount of memory that you need. Only load things that you actually require at the time that you need them, and release them when you're done, so that you don't actually get into the situation where you're using almost all the available memory. But if you find yourself there, the system's going to tell you about it, and you can respond to that in your view controller or your application delegate. And if you don't, you're going to be terminated.
How do you know when you respond to the warnings that you actually have released enough memory to actually not be terminated?
Sure. So the question is, how do you know when you're responding to these warnings that you've released enough memory to not be terminated? And basically, you actually get more than one shot. So we'll ask you a second time if you didn't release enough the first time, which should be a hint that maybe you didn't do enough. You won't be terminated immediately after the first one, although that can vary. I mean, if the reason that you're being asked to free some stuff is that you're actively allocating a lot of memory, and if you just keep doing it, if you do it fast enough, you may not even have a chance to get the next warning because you fill up all the available RAM before we even would have a chance to notify you. Then you're just going to get killed.
So another question.
Mm-hmm.
What about what if you write a program that sort of would work on a newer iPhone that has more memory, twice as much memory or something, and then the app just doesn't work because of those memory issues on an older iPhone?
All right, so the question is, what if you write your application and you test it on a new iPhone, which has more memory than the original, and everything's looking great, and then it can't quite run on the old one because of these issues? You probably want to test on the original iPhone as well. You can actually specify that your application requires the newer hardware, but you're limiting the set of people that can run it. So it's kind of it's a choice that's sort of left up to you. If you really don't think that you can write your application to work in less memory, you can prevent it from being installed on older devices. But I mean, there's a lot of people that have these devices, so not the ideal thing to do. All right, so the first thing that I mentioned that we'll want to talk about is loading things lazily. It's pretty pervasive throughout the Cocoa frameworks, and a lot of the APIs that you're going to be using actually encourage this type of behavior. So UI table view, for example, when it's asking for the rows, it doesn't ask you for all the rows that are in the table view up front. It only asks you for cells for the rows that are currently visible. You probably want to take advantage of that and not go off and just load a ton of memory, big files off disk for all the rows in your table view. Just load the pieces when table view asks you for them. So yeah, only really do as much work as is required. And as I mentioned a bit ago, this is also a pretty big consideration for application launch time. Users really expect on the iPhone that when they tap their application on the home screen, they see it animate up, and it should become responsive and interactive almost immediately. Users really don't want to sit there and wait for a loading screen or watch a spinner go around. They really want to just get started using it right away. So if you're loading a bunch of stuff up front, that's not really going to work. And also, there's a built-in limit on how much time you have to finish launching to kind of encourage this type of behavior. If your application takes too long to finish launching and doesn't complete the application did finish launching method, you'll actually get killed before you even get a chance to keep running. So you really want to make sure that you're not doing too much work when you're launching, or you're not going to like the result. So yeah, really try and think about where your code belongs. Don't just throw all the initialization code in application did finish launching. If you have multiple view controllers and each one needs a different piece of data off disk, try and move the loading of that data into view did load or view will appear, rather than doing it in application did finish launching. That way, if you've got a tab bar, you only load the data for the tabs that aren't visible when the user actually taps them. And use multiple nibs for your user interface. Again, if we're talking about this tab controller, you could go ahead and throw all the subview controllers into the tab controller and then throw all the views into there and do it all in one big nib. And that probably seems like a pretty interesting thing to do. It's most people's natural reaction when they see interface builders. I want to build all my user interface in this one nib because then I can see it all and lay it all out. But the implications of that are everything we just talked about. All of it has to load right away at application startup. Everything's in memory for the lifetime of the application. If you can break it up and have each view controller have a separate nib, the application has much more control and much more granular control over its memory usage. And we'll talk a little bit about what view controller can do for you in this case. But it's really the way you want to design things. Every view controller should really have its own nib, not throwing everything into one main nib. So yeah, here's an example of loading something too early. We just kind of talked about this. If it's not needed until much later, don't do it in your init. If you're initializing this view, but maybe I'm assuming this is a view, but maybe it's not because it's not init with frame. But if you don't need this data right now, some huge image that we're getting off disk, don't load it in init. Let's hang on to it and do it lazily. So if we have an accessor on our object for myImage, maybe we'll have an ivar called myImage on our object. And then when some other code accesses that ivar through the accessor, this is probably a property, and since we don't have a setter, maybe it's at property read only UIImage myImage. We can implement our own accessor, and in that check to see if myImage is nil, which it will be because all ivars are nil by default. We talked about that early on. And if you forgot, we did talk about it. Every ivar in your class is initialized to nil, so that's pretty convenient for things like this. In your accessor, we'll just check to see if it's still nil, which would indicate no one's called it yet. And if that's the case, we'll read it off disk then. So we won't try and load the image until someone needs it. And you'll find this is a pretty common paradigm throughout all of UIKit, and actually a lot of the foundation classes and a lot of what we do on Mac OS X and iPhone OS. One thing to be careful of, well, yeah, it benefits memory and launch time. We kind of talked about that. Is this is not thread safe. So if you can consider that you've got two different threads that are both trying to call myImage at the same time. Let's say the first one gets in here, it checks to see myImage is nil, but then the scheduler interrupts it and schedules the other thread. So then the other thread comes in, it also sees myImage is nil and gets in there. And at that point, they're both going to try and load the image off disk and both assign it to the same ivar. One of them is going to get leaked because the ivar can only hold one value at a time, obviously. It's the same object. It's not safe to do that. So if you're going to be doing this kind of thing and accessing myImage from multiple threads, then you're going to have to start doing some kind of locking, which we talk about a little bit later. But in the general case, if you're only accessing it from one thread, probably just from your main thread, or just from a background thread or whatever you have, it's a good pattern to follow. So we just mentioned that in that case, you could end up having a leak. So how would you find that? Well, we'll talk about that in a second, but basically, memory leaks are bad. I think that pretty much goes without saying, but we're going to say it anyway. You don't want to leak your memory because it just starts accruing in memory and no one will ever release it. And eventually, you're going to have these application termination things going on. Because even when you get the low memory warning, you no longer have a reference to the object that's been leaked. So you can't even free it even if you wanted to. But luckily, they're easy to find with the right tools. And we've got some great tools for doing that. Things to keep in mind when trying to figure out why you might be leaking, and a lot of these things are stuff we already talked about. Take a look at the method names. Alloc, copy, and new return retained objects. The convenience methods return auto-released objects. We've been talking about this all semester, so hopefully everybody's pretty comfortable with it by now. Balance your copies to alloc copy and new, and also retain with calls to release. Basically, just manage your retain count. Make sure that they always go down to 0 when you think they do, and that your objects are actually getting deallocated. One case where this often bites people is in early returns. So if you've got a method implementation, and at the beginning of that method you allocate some object, and you think when you're writing this method, I'm going to be on top of things. I'll immediately put release at the bottom, so I know that I don't have to forget about it later. I've got my allocs, I got my release, and I can write code in the middle, and I'll be fine. I already wrote the release. I'm good. If you then somewhere in there have a conditional check and say, if not this condition, return, well, then you're not going to run the release at the bottom anymore, and your retain count just got out of sync. So be careful of early returns. It's actually, early returns inside of a method are things that we try to be pretty careful to avoid when we can. It kind of is a personal preference. It's sort of up to you. But in general, I try to avoid doing early returns. I think Al pretty much agrees with that one. The only time that I'll really write an early return into a method is if it's the first thing I'm doing. So if I'm getting a message and I want to validate that the input is valid for this method, I might check right away, is my input not nil? And if it is, then I'll just return there before I've done anything else. But if I've started allocating objects or doing anything else in the method, it probably won't return. I'll try and do that in conditional statements to control the flow without requiring a return. And goto is another kind of serious issue in this case. Hopefully no one's too big on that. If you are, I'm sorry, but this isn't basic. So yeah, what are we going to do to find these leaks? Well, there's actually a great tool called Instruments that's included with Xcode and all the development tools. It's installed by default, so you already have it. And there's a way that you can get to it right from Xcode. There's in the Run menu, there's Start with Performance tool. And in this case, to find leaks, obviously we want to start with the Leaks tool. And actually, let's just take a look at what this is going to look like in, sorry, what are we talking about here? Now let's just take a look at it. It's going to look like this, but we'll see that in just a second. Oop, I lost my folder here. All right, so I've got a project that I already created. And I'm pretty sure I've got a leak, possibly because I have a comment saying I have a leak, but let's assume I didn't have that. We'll call Run with Performance tool here and go with leaks and see what happens. All right, so I'm running along. I've got leaks running in the background here. You can kind of see it launched it for me. And there's a little bit of user interface here. There's the object alloc tool, which we'll get to in a minute. But the interesting part here is the leaks one. And the timeline up here, if you're used to sort of audio tools or anything that gives you a timeline view, it shows you basically the state of your application and its leaks over time. So I just hit the record button there, which actually stops the recording and actually ends the execution of our program. Our leak was up front, so I already know it's leaked, and in fact we can already see it here. So no need to keep running, I already stopped it. So now we can go back and look over time and find where our leak was. And if you take a look at this bottom timeline here, the top half of that is number of leaks discovered. And there's a big red mark right there that shows us where it found some leak. Now, one thing to be careful of with this is that leaks isn't something that runs constantly through the execution of the program when you're using it. It runs at a particular time interval, and the default is 10 seconds. The reason for that is that it actually has to look through the entire heap of your application trying to see if there's anything leaked. And it actually can be a pretty expensive operation for it to do. So it can't really do it continuously. It does it at discrete points. You can actually modify that by changing the duration to be less or more. Or you can check at a specific time by clicking Check for Leaks Now. But anyway, you want to make sure that it's run long enough that it's actually done a check. So in this case, we did.
Can you zoom in a little bit?
Oh, yeah, sure. Sorry. Let's zoom in here. So yeah, up here we've got our leaks tool. We've got number of leaks discovered, and there's that red mark that shows us there was one. So if we look down here at the middle section of this screen now is going to show, geez, I know how to use this really, is going to show just a little, is going to show the leaks that we actually came up with. So in this case, we've got an NSCF string. I'm not sure what that one came from there. Core graphics. That one I wasn't expecting, so we'll pretend that that's not there for a minute and just take a look at the string one. There's a couple ways you can do this. One of the things I like to do is click on this button at the bottom here, which brings up this extra view on the right-hand side, which actually shows you the stack trace of where the leak had come from. So one thing to keep in mind here is that what leaks is going to show you is the call site of the allocation of the memory, not the call site of the leak, because the leak is, it's unclear what caused the leak. That's kind of up to you to figure out. It's going to show you the object that was leaked, but you have to figure out why that was leaked. So in this case, let's take a look. The place where this actually got leaked is somewhere under UI application handle event. So we were probably handling some event. In this case, we were initializing. The my table views application did finish launching was called. Add subview. Oh, view will appear is the thing in our application that's at the top of the call stack here. It's probably where the thing was leaked. And in fact, right after that is a mutable string init. So let's double click on that. It's going to bring up our code right here in the instruments tool, and we can take a look. And in fact, it's highlighted the line where it thinks that the leak happened. So if we take a look at this code, what are we doing? Well, we're getting an NS mutable array, and we're doing it with the convenience method. So retain count of 1 already auto-released, so that's all right. We are calling NS mutable string alloc init, so we've got a retain count of 1, but not auto-released. We're adding that object to the array, so now retain count on the string is 2. And that's it. So when we return from here and the auto-release pool pops, the array is going to go away because it was auto-released and had a retain count of 1, so it'll go away. It's going to call release on all of the objects that were in it. So one of those is the string, but the string was already at retain count 2, so that only takes it down to 1. So actually, we just leaked this object because we have an extra retain count, and we no longer have a pointer to it anywhere because the array's gone. So if we want to fix that, we really want to. Oops, sorry, you can't edit in instruments. So let's switch back to Xcode and come to our view will appear. So we're adding a string to the array. The array retains it. We don't have to keep that original retain count here. So now that we're done with it, we really want to call string release. If I can type it. So now if we go back to run and start with performance tool leaks. Let's go over here and force it to check for leaks right now. Looks like we're good. Bring that. There we go. Ignoring, of course, these core graphics objects that seem to have gotten leaked from somewhere else. But that's not part of the plan. All right. So that's how you find and fix leaks using the leaks tool. And it's actually really cool. It shows you right, exactly where the object was allocated. So a bit of work left after you, especially if there's some more complicated logic. If that object that's getting leaked follows a really complicated code path and you put it in lots of dictionaries or something, you kind of have to spend some time figuring out where your retains and releases got unbalanced. But at least you know what object it was, so it gives you a really good starting point. And sometimes it's even easier than that, like this. It's very clear why it was being leaked. All right. Yeah?
What do different colors on the right column mean?
All right, so the question is, what do the different colors on the right column mean? The column for the backtraces there are actually color-coded by library. So every frame in that backtrace, it has a different color that corresponds to what framework or application that particular frame was in. So actually, I don't know if I still have that up. Yeah, OK, so in this case, the yellow one is DYLD, which is the dynamic loader. It's the thing that basically combines your application and all the libraries and links them at runtime. So that one's yellow in this case, and all these things are in DYLD. Purple in this case is in core graphics. Lib system is the red one. Graphic services is this sort of a tan one. I don't know. Green is UIKit. So everyone's a different framework. In the case of our application, that's this one. That's this bluish color. I'm not sure actually if the colors are always the same for your application. I think they're kind of random. But basically, you can find one frame that's your application, and all the other ones with the same color will be your application. Usually, it's the thing at the top of the stack here that is from your application where the leak came from. This one is not our fault. Something else is going on with that. All right. Any other questions? OK, so the other thing that we want to talk about here is auto-release. And I already alluded to this a little bit and talked about a little bit what we're going to see, but let's go into some specifics. So auto-release is great, right? It really simplifies your code. You don't have to always make sure that at the end of your function you call release. You can just call the convenience method, and you'll get back an object that you know is going to go away for you. You don't have to worry about the specifics. So it gives you a little bit less concern about the scope of the lifetime of objects. But that lack of concern can sometimes come back and bite you. So when an auto-release pool is drained, that's when it finally calls release on all the objects, right? So those objects will not go away until the auto-release pool drains. And in the normal case, for the auto-release pool that the system has set up for you, it's not going to drain until you go back to the run loop. So after you finish processing your touch event, it's not going to get drained until you return back to the run loop and finish processing that touch event. So any object that's created and auto-released during that time is going to stay resident in memory up until you return from your processing. So yeah, that's the one that's created automatically at each iteration. So yeah, what's the catch here? If many objects get auto-released during this time before the pool is popped, the amount of memory that those things required is just going to keep going up and up and up because they're not going to go away until the end. So that kind of leads to this kind of situation. It's not really the most fun to swim in there, probably. So don't really want that. So how do we avoid that? Well, you've got this high water mark, right? It's the largest amount of memory that's needed during the processing of whatever it is you're doing that's using this auto-release pool. You want to get that high water mark down. So basically, you want to make sure the pool is continually drained while you keep throwing things in it if you're going to be throwing a lot of things in it. So you can do that by creating and releasing your own pool. You don't necessarily have to wait for the system to do it for you. You can scope it a little bit more on your own. It's usually not necessary. In most cases, you're not creating so many auto-released objects that it really is that big of an issue. But don't just go throwing them everywhere. But if you use the tools we're going to see in a minute, and if you see that you have a problem, go ahead and try and take care of it by being a little more careful about your auto-release scoping. So yeah, the tools can help you identify it. The classic case where this comes up is tight loops. You've got a loop and you're iterating over 10,000 objects, and every time you're auto-releasing 18 objects, all those things are accumulating in your pool. So you might want to try and be careful about scoping this pool within the loop. So let's take a look at an example of that. If we've got an integer, and let's say we're iterating some large number of times, so say 10, 20,000, and within that loop, we're going to get a string, call a lowercase string on it. So lowercase string gives us an auto-released object that is the lowercase version of that, and then call string by appending string, and maybe pass in some arguments there. That's going to give us another auto-released object, and then we NS-log it. That's fine. But now we've just created two auto-released objects right within there. And the memory for those isn't going to go away until this entire loop is finished. So we might end up with 20, 40, 80,000 objects if we're doing this a large number of times. And the memory usage for that can get pretty big. So how do we want to take care of that? Well, you could create an auto-release pool yourself for every iteration. So in this case, let's start out our loop with NS auto-release pool alloc init and finish it with pool release. This could also be, it's an equivalent to pool drain, which we've also seen in other cases. They're really the same thing for the purposes of this. It only becomes interesting with garbage collection on Mac OS X. But yeah, that's not a concern here. So that's going to take care of the problem, but it's pretty heavyweight, right? For every iteration of that loop now, we're allocating and destroying one of these auto-release pools. It's kind of possibly more than we need. We'll see in a minute what we might do about that. Basically, we might just want to do it only every 100 times or every 1,000 times. Pick a number that's a little more reasonable than every time. But so what if we need objects outside of that loop? Well, we could actually still do almost the exact same thing, but retain the object within the loop, right? If the object is auto-released already, if we put an extra retain count on it, when the auto-release pool is popped, that retain is still going to be there, so we can get to it at the end after the loop and probably auto-release it again since we're returning it to someone else. So even if we're scoping our own auto-release pool in there and we've got some auto-released object that we want to hang on to, we can still do that just by adding an extra retain count of our own. So another option, and this is, I'm personally in favor of this in general, but you'll find opinions vary pretty widely. Personally, I prefer to avoid auto-release if I can. If I can scope my memory usage on my own, I usually do that. For instance, I'll probably call NSString alloc init with the format, and then call release myself so that I know when it's going away, rather than calling NSString string with format, which gives me the auto-released object. It's really it's personal preference in the end. And the auto-released one, there's no doubt it's convenient. And in some cases, you really can't avoid it. If you need to return an object to someone else, you may have to do this. But within your own method, scoping your memory usage, it's a pretty good idea, especially on the embedded device where you really want to keep tight control over how much memory your application is using. And then you don't have to worry about these high watermarks on auto-release pools because you're managing the memory yourself and you know when it goes away. So yeah, when it makes sense, switch to alloc init release. If you can do it, it's a great thing to do. It helps to rein in your memory usage and make sure you really have control over what's going on. So another option is in the previous example that we just looked at there, instead of calling string, lowercase string, the convenience method to lowercase the string, and then calling string append with format, you could just use a single NS-mutable string for all of those operations. Alloc init an NS-mutable string, set the string on it. NS-mutable string can also lowercase its contents. It also has a method to append an additional string with format. So you can do all the operations that you were doing with the single NS-string convenience methods, but on one object, the NS-mutable string, which doesn't allocate any of this temporary memory and start auto-releasing things. So it avoids the problem entirely in a slightly different way. All right, so let's take a look at what this is going to look like and how we'd find these things if we actually have one of these high watermark problems. Close up my last example and bring up the next one here. So in this case, I've got a UI table view, and well, let's just run it first and take a look. It's not too interesting. It's pretty much the same thing that we just saw. Got a couple of names in a list there. But I've got a lot of work I need to do at the beginning here. So let's, oops, where'd that go? And view will appear. I have to do this thing 10,000 times. I really need foo lowercased with something appended to it. I really want to make sure that that's the same every time. So we're going to call it a lot. Should probably append something on there. So we're going to end up with a lot of memory. And obviously, you probably have this exact same code in your own application because it's pretty useful. So let's take a look at what happens. All right, so in this case, we're looking at the object alloc instrument, which is up at the top here. And you can kind of see already, we've got this big spike in our graph, right? So we're pretty much already done sampling. We've run that iteration. Let's stop it. And now you can kind of step through here just by dragging up in the timeline at the top and take a look at the total memory usage that your application has at all these different points in time. And we can see that after that 10,000 iteration, we just spiked at 1.3 megabytes worth of NS strings for great reason, I'm sure. And we kind of leveled off at 470 some kilobytes. It may go up a little bit, but basically this is the point where the pool got drained, right? Once the pool drains, all those temporary objects went away and everything got released. So let's go down here and take a look. This is going to be, this middle section now for the object alloc instrument shows us all of the objects that have been allocated over the entire lifetime of this application. And they're sorted by count or whatever. You can click on here to sort them by whatever you want. In this case, we can see CF string. We've got 1.14 megabytes worth of them. And for an overall count of 41,941, that's pretty good. And over on the right, the number of allocations graph is even slightly more interesting. It shows you, in the darker color is how many of those objects are alive right now. And the lighter color is sort of the high water mark of how many of those objects there were alive. So in this case, we can see we had a ton of them at some point, but there's only a few available that are left right now. So we can still get similar information about this. If we click on, sorry, maybe you didn't see what I did there. If you point to CF string in here, you've got this little arrow next to it. You can click on that to drill down into it. And this is going to give us information about backtraces of every single one of those objects that got allocated anywhere in our program. So let's sort them by the responsible caller to just try and get a little clearer picture of what's happening here. So we got a bunch that came in from bundle with identifier, but not too many. That's probably okay. We got a bunch from localized string, but now we've got this whole mess of them from NS placeholder string and it with C string. So it seems like something might be amiss there. So let's click on that and check out again our backtrace on the right. So we can see the topmost frame on the stack that came from our application in this case is this guy. Let's click on it and get the source code again. Here we've got string by appending format, 2.17 megabytes worth of those guys. Probably not something that's such a great idea. So we can go back and try and fix it the way we were just looking at, right? The first thing we can do is allocate our auto-release pool within the loop. Oops, UI, NS auto-release pool, alloc init, and then at the end of the loop, we'll drain it. So if we do that and run with the performance tool leaks, sorry, object allocations, we could actually run with leaks too, because that also gives you an object alloc instrument. Now we're getting to this case where we're running, but we no longer have that huge high water mark. It's pretty much leveled off right away. So So, and that's a pretty good thing because we're not wasting all that memory all at once. And if we had ended up allocating too many objects, the system would have just destroyed, killed our program because we had no way to release them, even if we got the memory warning. They were just sitting in that auto-release pool. This may be a little overkill. We mentioned that maybe you want to do this not quite as often. So you could instead allocate your pool outside of the loop and drain it outside the loop. And then within the loop, maybe you only drain it once every 100 times. So we could say if I mod 100 is 0, then pool drain, and create a new one because we just drained it. So we're creating one at the beginning. Every 100 times through the loop, we're going to drain it and create a new one. And then when we're finally done, we'll drain the last one that was left. Probably a little bit more reasonable. 100 iterations isn't that bad. We weren't creating that many objects. So yeah.
How do auto-release objects know which auto-release pool to go into?
So the question is, how do auto-release objects know which pool to go into? And they always go into the topmost pool. So it's kind of a stack of pools. And every time you allocate a new one, the new one gets pushed onto the stack. When you drain it, it gets popped. So yeah, always the topmost one gets it.
What if you lose the pointer to your pool? Is there any way to, since they're being kept in a stack, somewhere to find out what the topmost pool is?
So the question is, what if you lose your pointer to the pool? Can you get the top item off the pool stack? And you can't. No, you really want to hang on to it. And actually, a specific of the implementation may be that it's OK to call drain twice on the same pool.
I don't know. I just ran into a case where I leaked an auto-release pool last week, and it wasn't good.
Yeah, basically nothing good can come of it. You really want to make sure that you hang on to it, because otherwise you're potentially leaking a large number of objects from it. Yeah, be especially careful with draining your pools. All right, so that's pretty much that. Let's get back here. All right, so next we've got the overhead of object creation. And this is pretty much the thing we talked about with table views when we're dealing with reusing objects. And this isn't always the case. I mean, object allocation isn't inherently bad. But you may find that you've got some object that has a lot of associated data with it, and the cost of creating all that data is high. And you need it a lot of times, but with just one parameter changed. Rather than freeing it every time and creating an entirely new object with that new parameter, maybe have a property for the one parameter that needs to be changed and reuse the rest of the object. So yeah, like I said, most of the time allocating, deallocating, not a significant issue. But there may be times where, and you can find this with some of the performance tools. We're not going to look too deeply at Shark right now, but I think you guys showed that on Friday the first? No? Oh, sorry. Well. Shark, it's great for finding these kinds of issues. We won't look at it too much right now, but basically, if you find that you're having a performance issue and you've identified that it's the creation and destruction of these objects, you might want to go ahead and try and avoid this kind of thing then. So if my object is really expensive to allocate, and then you just need it 10,000 times again, maybe change it to something like this. So, oops, everything we just talked about there. So allocate the object outside of our loop, do the loop 10,000 times, and just change the value property on my object before telling it to do something. Because maybe setting that one property isn't very expensive, and you can just change that rather than getting new objects every time. Again, not something that you probably have to worry about all the time, just something to kind of keep in mind if you find you're having some performance issues. Think about it, but it's probably not the most common case that you'll run across. And DQ reusable cell with identifier is an example of that. And one of the reasons it's such a big win for this case is that the cost of the cost of the creation of table view cells is almost entirely in the creation and initialization of the backing store for it. So the creation of all of its subviews and all of the memory that is drawn into for all those subviews, that can be really expensive. But the cost of just redrawing a single line of text in it is not very much. It's dwarfed by the cost of allocating the entire cell hierarchy itself. So if we can reuse the entire table view cell and all of its subviews and just redraw a line of text in it, that's where we get the performance win from DQ reusable cell. It's really the creation of that object that's actually pretty expensive. So not the most common case, but places like this, it does come up. All right, so if all this fails and we're still leaking a lot of memory and we've got auto-release pools that are creating 1,300 megabytes worth of stuff, you're pretty much in big trouble. So if that happens, then you're going to get a memory warning. So you have to keep in mind that when your application is running, you're actually coexisting with system applications that are running at the same time. The user may be playing audio, they may be downloading some mail, they may have some web pages open, so there are other applications running on the phone, even though there's only one third-party application running at a time. So you do want to respond to these memory warnings, or as I mentioned, consequences are pretty dire. Pretty much your application gets killed. So if your application is the guy in the middle there, and you're getting a memory warning, and you're not responding right away, the first thing that's going to happen is the system is going to kill processes that are running in the background. So your application may not die right away, but the user's not going to be too happy because their music's going to stop playing and their mail's going to stop downloading because the system's going to blow those guys up first and try and allow the user to keep interacting with the app they're using. Now, if you still don't respond to your memory warnings and the system's done everything it can to try and give you as much memory as you can and it's kind of down on its knees begging you to stop, and you just still don't do it, well, then your time comes. And that's pretty much the end of that. So definitely want to respond to these memory warnings, both to avoid having your application get killed and to keep the user wanting to use your application. Because if every time they run it and they're on their jog and listening to music, it stops playing their music because you're not responding to memory warnings, they're probably going to stop using your app. All right, so you want to respond to these warnings. Every view controller did receive memory warning. It's a method you can implement on your view controller subclass. And this is called automatically for you if the system finds that it needs more memory. By default, UI view controller will release the view that it loaded in the case where it's not on screen. So if you've got a tab bar controller and the user has actually tapped on all 3 of the 4 or 5 of the tabs in there, so all those views got loaded, when a memory warning comes in, the system, well, the view controller actually itself, in the default implementation of did receive memory warning, will release all the views for any of the view controllers that aren't the one that's currently visible. So if the view's not on screen, it's a candidate to get released. And that can actually save quite a bit of memory. Although it is important to keep in mind that can happen because the implication of that is that view did load on your view controller can actually get called more than once. In the general case, you'll probably write code and think, oh, view did load, it's called once when the view's loaded. I can do one-time initialization in there. That's actually not true because of memory warnings. If you get a memory warning and the view gets flushed, there's actually another method called view did unload, which you can implement. And that's called after the memory warning happens and the default view controller implementation releases your memory, and your view, sorry. It'll call view did unload. So you might have to also clean some extra things up in there so that it's safe to then call view did load again. So yeah, by default, it releases the view if it's not visible. You probably also want to subclass this and override did receive memory warning and release any other expensive resources you've been holding on to. So if your view controller has a really big picture it displays, or a list of users or a list of photos, not that we'll be seeing that anytime soon, and you're caching those and hanging on to a lot of them, if and you did receive memory warning, you might want to release that cache if you don't need it right now. If your view controller is not visible, release all that memory. You can load it again. Basically, you want to get rid of stuff that is easily recreated. If it's something you loaded off disk, so you can very easily load it off disk again if you need it later, just release it. And if you have that stuff stored in an IVAR, release the IVAR and set the IVAR back to nil so that your accessors can do what we saw earlier and check to see if that value is nil when they're called next time and reload the resource. So that'll look something like this. Did receive memory warning. First thing you want to do, call super did receive memory warning to get that default implementation from UI view controller, and then release your expensive resources and set the value back to nil. The other place you can do this, if you don't have a view controller and you've got some global data that's stored outside of your view controller, is the application delegate method. Application did receive memory warning. So pretty much every template that you create in IB in Xcode will give you an application delegate by default. You can just go ahead and implement this on your app delegate and release global resources if you have them, although you probably shouldn't have any global resources. So. Encapsulation. All right, so what other resources do you want to release? Well, like I said, things that you can load off disk. If you got a lot of images you're loading from files, get rid of those. Sounds, cache data. If you can get it back, get rid of it. The other thing that you can do to sort of take advantage of some built-in functionality that manages memory pretty well for you is by making use of SQLite and core data for large data sets. Probably actually more the core data side than SQLite. SQLite leaves a lot of the memory management up to you. But basically things that allow you to load data from large collections of data, but in small pieces. You want to avoid having your 40 megabyte plist that you load in one call at the beginning of your application that gets stuck in memory the whole time. If you've got something that's that large, break it into smaller pieces, store it in a core data database, something where you can load just parts of it at a time. And there's actually some really good documentation on all this stuff. It's available at developer.apple.com. It's one of the conceptual docs, and so it's under there in managing memory. All right, so that's pretty much all we're going to talk about with memory management and that kind of stuff for performance. So the next big issue that I want to cover is concurrency. And this gets into what we saw at the end of class last week, or sorry, on Tuesday actually. The example Chris gave when he was scrolling his table view, and every time a new cell came in, the scrolling stopped and paused until the data was available and then kept going. So we want to talk about how we can avoid that kind of thing. And the solution that we generally end up using on Mac OS X, or sorry, iPhone OS, is concurrency. So with a single thread, and by default your application is single-threaded, you've got a main thread. All your processing that you've been doing so far has been happening on that main thread. If a long-running operation comes in and starts taking a really long time, the user can't interact with your application, the system can't update the screen for your application, no drawing can happen. Basically, to the user, it looks like everything just stopped. And that's a pretty bad experience, so we really want to avoid it if we can. You want to make sure that your application stays as responsive as possible. And an example of where you see this kind of thing is like in Google Maps, the default Maps app built into the iPhone. If you scroll the map really fast, before the phone has actually had a chance to download the new map tiles off of the Google servers, it's going to prioritize user interaction over visual correctness. So the map will keep scrolling, and maybe you'll get some blocks showing up that don't have actual content, and they'll fill in as the data comes down over the network. You really want to prefer interactive consistency to visual correctness is pretty much what I'm getting at there. Make sure the user can always do something in your application. If they're touching it and nothing's happening, they'll feel like it's unresponsive. They're going to try and kill it. They're going to want it. It's not a good user experience. It just feels broken. So one of the ways that you can avoid this kind of thing is by using multiple threads to load your resources or perform your expensive computations, so that you can basically block in a background thread that's not interacting with the user and keep that main thread available for user interaction. So threading on the iPhone is actually using the standard POSIX threading API. You can get that header in user include pthread.h. This is a C interface. It's pretty much a Unix standard. It's very common. But for the most part, when you're dealing with these things in Cocoa, you don't really have to work with the pthread implementation directly. There's some pretty nice wrappers around this implementation that are provided by Foundation. That's all object-oriented and lets you do threading with your objects really easily, actually. It's pretty great. So the class that controls a lot of this is NSThread. And there's actually even wrappers around this that make it even easier. But NSThread is kind of the basic basic interface to all this stuff that you use through Foundation. It creates a run loop for you automatically. We haven't talked about run loops a whole lot. You may have heard both Al and myself mention from time to time when you go back to the run loop, or this all happens and your pool drains when you get back to your run loop. Basically, I can't actually think of a concise explanation for what a run loop is. You have a...
There's the application event model that we showed.
Yeah, that's true. We showed early on in some of the early slides a model that basically it was a line that went from application did launch back to the run loop, and then it looped in there processing events. So every time an event came in, you'd go out, process that event, and then return back to the run loop. It's where your application spends most of its time. Usually you're sitting in the run loop waiting for the user to do something, or for some data to come in off the network, something that would kick you out to do some processing. You do it, and then you get back to the run loop. When you create a new NS thread, that thread gets a run loop created for it automatically. So your main thread's in a run loop, your other thread is in a run loop, and they can process things independently of each other. Your NS thread does need to create its own auto-release pool. The default run loop on the main thread has an auto-release pool that's pushed and popped for you automatically. But on a background thread, if you're getting some processing coming out of your run loop there, you actually have to create your own NS auto-release pool in that case. There are some convenience methods then that let you do communication between these threads. Basically, your application on your main thread may be blocking in the run loop, waiting for something to finish on your secondary thread. So there's some methods that provide a convenient way for that secondary thread to send a message to the main thread to kick it out of the run loop and get it to do some processing. So we'll take a look at those in a second. Your typical case for using run loops is basically if you've got some long-running operation and you're on your main thread and you want to kick it off to a background thread to happen while the user can keep interacting on the main thread. So the way you would do that is just by calling nsthread detach new thread selector with target object. And this creates a new thread for you. That's really all there is to it. And it'll automatically call the doWork method in this case on the object itself. You can pass an optional parameter object. In this case, we'll pass some data. But yeah. The question is, if you wanted to pass in multiple arguments, what would you do? I don't think there's actually a version of this that takes more than one argument, is there? No. So you pretty much end up having to define your own object that contains other objects, or allocate an NS array and stick them in there, or a dictionary and key them. If you need to pass multiple parameters, you can put them in one of the collection classes and pass the collection class as your one object. You just kind of have to define the interface between the caller and the method being called in selector so that it knows how to unpack the data that you packed up for it. Sorry, someone else? No? All right.
Target always self?
Question is, target always self? It often is, because usually if you're detaching a thread to do something in the background, you're probably dealing with data or the object that is detaching to do the work. But it doesn't have to be. It could be anything. It's any object. So basically all this is going to do is start a new pthread in the background. And it's the same thing you could do on your own if you took a look at the pthread library. It creates a new pthread, starts it running with a default function, which then calls into this method. So it could be any object. It doesn't really matter. So then your doWork method would probably look something like this. As I mentioned, you have to create your own auto-release pool because you won't get that from nsthread. So we'll do that. We'll call do lots of work on some data, some long-running operation that's going to take a while. And then when we're done, we want to message back to the main thread. Maybe not always, but usually. You're going to want to call back to the main thread to tell it that you finished whatever this work was. Maybe you're loading something off the internet so that you can populate your table view cells. You want to message back to the main thread because all interaction with the user interface has to happen on the main thread. The UIKit framework, when you're dealing with UIKit objects, views, and updating strings on labels and that kind of thing, that all has to happen on the main thread. So in this case, we'll call perform selector on main thread, which is a convenience method on, actually it's on NS object. So we can call it on self. So we'll call self perform selector on main thread. The selector in this case will be all done, and the object will be some result that we got. There's an optional parameter at the end called wait until done. This basically determines whether the place where you're calling this from will block until the method being called finishes. There's not a whole lot of great examples of why you'd actually want to block for that. I actually can't even think of one off the top of my head. So usually it's no. Maybe you can come up with some case where you'd want it to be yes. Sure.
Is that like for pthreads, sort of like a join? Does that have the same effect as join in terms of waiting until the thread is...
So the question is that like pthread join? And I'm actually not super familiar. Pthread join causes it to block until the other thread completes. Is that correct?
Join waits for the other thread to go, but it doesn't block.
Join doesn't block. I actually don't know the answer because I don't know the semantics of pthread join. So we can talk about that after if you want.
Sorry, what does that do again? What is the wait until that?
Oh, so it would. So at this particular site, basically the call to the method perform selector on thread with object wait until done wouldn't return until the all done method finished executing on the main thread, if this were yes.
Okay, then it does do the same thing that Join does.
Yeah, it would block the, basically pool release wouldn't get called until after this finished.
Maybe if the operations happening at all done aren't thread safe, then you wouldn't want two all dones to be happening at the same time.
Yeah, that's true. So the point was maybe if all done isn't thread safe, you wouldn't want two to happen at the same time. But this doesn't necessarily guarantee that, because if you had detached two separate threads with the same selector, the other one might also get to the same point. Okay. And in fact, the thread safety of all done would not really be that important in this case anyway, because you're performing selector on main thread. There is only ever one main thread, so that's kind of a bottleneck in and of itself. If two threads are on the background, both calling perform selector on main thread, wait until done, regardless of the wait until done, the main thread can't possibly be in two calls to all done at the same time because there's only one main thread. Okay, so UIKit actually, as I mentioned, is not thread safe. So I mean, there's a lot of different definitions of thread safety, and I'm sure you have had other classes where you've talked about it. UIKit's not really thread safe in any of those definitions. Basically, your objects have to be created and messaged on the main thread. When you create a UI view, you have to create it on the UI on the main thread. You have to add it to your view hierarchy on the main thread, change its properties on the main thread. Basically, you'll hear main thread a lot when you talk about that. I hesitate to even say that one. You can create a UI image on a background thread. Kind of goes against what I just said, but there are some operations that are kind of thread safe. But you can't set it on an image view, so there'd be very little benefit to creating it on the background thread anyway. Basically, your user interface code has to be running on the main thread.
But if you load an image from the internet, then, I mean, and you're doing that on a background thread, sure. What are you putting it into if you're not putting it into a UI image?
So the question is, if you load an image off the internet and you are not putting it, you load an image off the internet, what do you put it into if you're not putting it into a UI image on the background thread? Generally, when you're loading something off the internet, it comes down as an NS data, as the raw data. And the reason that slide was there is because I almost hesitate to even say it. I'm reasonably certain that UI image creation is thread safe. It is?
But
okay.
Displaying it in a UI image view would only happen on the main thread.
Right. So anyway, I suppose it's safe to create the UI image from the NS data on the background thread, but that's not really the expensive part of the load. The expensive part is getting it off the internet. So you could just pass the NS data to the main thread and create the UI image there too. All right, so, oops, went a little too fast there. Go back here and get our next threading example. So this is basically the same app that we looked at last week. Oh, sorry, that's the next one. This is a different one. We haven't seen this one yet. It's pretty new and pretty cool. All right, so what's the meaning of life, right? Let's do some calculation and find out. Well, now our button's kind of stuck. It's blue. I don't really know if anything's happening. How do I know if it's telling me the meaning of life? Oh, well, okay, it did. But it was a pretty bad experience, because while it was figuring out the meaning of life, I had no indication that it actually was doing it. For all I knew, it could have taken forever to find out the meaning of life. So we probably actually want to have a spinner that animates. In fact, I already had code to do it. I had created a UI spinner. Sorry, not a UI spinner, a UI activity indicator view. And I had told it to start animating. And I had even said that the button should hide. So why did none of that happen? Well, background thinking is where it was figuring out the meaning of life. And while it was back there doing that, it was sleeping for time interval 5 seconds. So basically, we were blocking the main thread for 5 seconds and not returning to the run loop. And because we did that, any drawing we did, any animations that we started, none of that stuff is going to start because we're busy blocking. It doesn't actually start updating your screen until you get back to the run loop. So really, we wanted to do that background thinking on the background thread because, well, we don't want to block the main thread. So let's call ns thread detach new thread with selector. And we'll do at selector background thinking to target, and we're going to self, because, well, that's what we were calling. We were calling self background thinking, so target is self. And this doesn't actually take a parameter, so we're going to say object is nil, because we don't have to pass anything. And we'll get rid of the call that called directly to it. So now Foundation is going to detach a new thread for us and run this method on the background. So if we build and run it now when we click start, the button hides, our activity indicator starts, and 5 seconds later when it's done, actually I didn't really take a look at that, but we were actually calling perform on main thread with did find answer, and the object that we're passing in is 42. And then did find answer stops the animation of the spinner and sets the text on our answer label. So yeah, this method here, the entirety of this, was running on the background thread. And we had to create our own auto-release pool because NSThread doesn't do that. And the sleep that was happening then was blocking not the main thread, but the background thread. So everything on the main thread could keep updating. We could draw things and start animations.
So what's set needs display not work? Like, you can't just tell it to update the view and then it would go do that and come back.
So the question is, would set needs display not work? And it would not, actually. So set needs display marks the view as needing to be drawn, but doesn't actually force it to be drawn. Anything that you call set needs display on in one turn of the run loop just basically marks it as dirty. So you can call it 8 times in that turn of the run loop, and it's only going to get drawn once. The drawing happens right before it goes back into the run loop. It's actually core animation is the thing that causes that to happen. It calls out and gets you to draw everything that's been dirtied, and then the screen gets updated. But without returning to the run loop, well, there are some things you could do with core animation that would force that to happen, but they're not generally very good practice, especially because you'd still be blocking interaction on the main thread. You really want to do it by moving your long processing to the background thread.
So child threads always have access to the main thread?
Sorry.
Do child threads always have access to the main thread?
Question is, do child threads always have access to the main thread? And yeah, I mean, the main thread it's a known thing. It's named. Foundation knows what it is. You can always get back to it from perform selector on main thread. Is that what you meant?
Is there a way to perform never mind.
So if I think I know where you're going with that, the attach new thread with selector is a convenience method that basically it returns, or rather it doesn't return anything. It starts a new thread. You can create threads that you actually have a pointer to, an actual NSThread object. And you can get back the current thread by calling NSThread current thread. And with those, there's actually some other, you can check it out. There's other threads other methods you can call on a particular NS thread. You can ask a thread if it's the main thread. Well, you can ask a thread, or there's also the difference between these two, right? So there's one with a plus and one with a minus. Which is which, and what do they do? Who can I call them on? Anyone? Oh, come on. What's the plus and what's the minus? Yeah.
So the plus should be just a class method as opposed to the minus, which is like an instance variable method.
Right. So the plus one is a class method. I can call NSThread is main thread. And the behavior of that is to say whether the thread I'm currently on is the main thread. The minus one is an instance method, right? So if I have an NSThread object, I can call is main thread on that and find out if that one is the main thread. So if I have an NS thread that's maybe some other I got and stashed somewhere else, I can check out later if it's the main thread. And in fact, you can always find out the NS thread that represents the main thread. So yeah, I mean, there are objects that wrap every individual thread, and you can deal with those with a bunch of different methods on here. And in fact, you can allocate and init your own threads and then start them executing. So we're running kind of out of time here, so I'm going to go through the last few things pretty quick here. Oops. So once you start dealing with threads, now you've got multiple things that, even though we only have one processor, so at the same time is kind of not quite the right thing to say here. You've got multiple things executing simultaneously, right? Concurrently, I suppose. On the desktop where you've got multiple processors, that can be a little bit more literal, where things can actually be happening at the same time. In this case, you've got 2 threads of execution that are interleaving their executions. The system is basically giving each thread a little bit of time to do its processing and then switching to the other one. And the points of those interruptions are not as well defined as you might hope. You might be in the middle of doing something and it just stops and lets the other thread start executing. So you don't have a whole lot of control over that. So in order to get a little bit more control over this kind of thing, you might have to start locking your data. And you've probably seen this in some of your other classes and operating systems, or I'm sure you've seen it somewhere. So I won't go into too much of the detail. But basically, Foundation provides an NSLock class, which implements a mutex lock, basically. And amongst other different types, there's actually a bunch of subclasses of NSLock that provide a whole bunch of different types of locks. I think there's a reader-writer lock and some other things. What's that? And a conditional lock. So basically, they let you protect critical sections of your code that can't be simultaneously entered on 2 different threads. Basically, if you need to update some mutable array, you probably want to, if that thing's going to be accessed from 2 threads simultaneously, you want to put a lock around the access and the update so that you can be guaranteed that only one thread is touching it at a time. So you might do something like this, NSLock alloc init, and assign it to an ivar in your initializer. And then when you go to do something that needs to be locked, so some method, you can only have one thread in some method at a time, we'll call mylock lock at the beginning and mylock unlock at the end. And then we know that anything that's going on between there, only one thread can be executing at any one time. Conditions are the other type of lock that we'll talk about really quick. NS condition, it's pretty useful if you've got a producer-consumer kind of thing. So you've got one thread that's producing some data and another thread that's trying to consume it. This is a little bit more complicated example. Sadly, we don't have too much time to talk specifically about it. But basically, in your producer, you'll start out that method by calling condition lock. And you'll produce some new data and set a flag that says it's available, and then call condition signal, which will tell the consumer that there's data available. So our consumer will have locked with condition locked. And then basically, it's going to loop on while is there data available. While there's no data available, it's going to call condition wait. And condition wait is actually sort of a collection of 3 basic behaviors. It's going to unlock and perform a wait. And then when the other thread signals it, it'll come out of that wait and try and acquire the lock again. And then it'll return from wait, and we'll be able to check new data exists. So you can actually have multiple consumer threads running at the same time. And only one of them can really pull something off at a time because the wait implies another unlock unlock, wait, and then lock. And and anyway, then when you're done with both, you'll unlock at the end of the method. So does that kind of make sense? I know it's pretty quick. All right. So wait is equivalent to unlock, sleep, and lock. The danger, of course, is that you can end up deadlocking if you've got one thread holding a lock and trying to acquire a lock that another thread holds, but that other thread's trying to, holds that lock and is trying to acquire the lock that the first thread holds. Neither one's ever going to, release it because they're both waiting for the other one, and now you've got a deadlock. There's actually, a lot of ways that you can end up in this situation. Locks can be pretty tricky to get right, so, got to be careful about that kind of thing. I'm going to skip through some of this because I think I only have a couple minutes here. So the locks can make your code hard to maintain. It can make things slower if you've got a lot of lock contention, multiple threads trying to acquire and release these locks all the time. It can really slow down the execution and progression of your code. So there's some alternatives to this kind of thing. And actually, alternatives to threading is maybe the wrong thing to say. Alternatives to explicit threading, sort of letting the system manage some of the threading for you. This is actually talking about, I'm trying to go so fast I forget what this thing in the middle was. So there's an NSURL connection. If you're trying to download data off the internet, this basically does it asynchronously. It lets the system manage the thread for you. And basically the system will do the download on your behalf and call you back in a delegate method when the download's done. There's timers that you can either have one-shot or recurring timers. So it'll call you back in some interval. Rather than sleeping for some period of time and blocking the thread, you can get called back later when you need to do something. Those things are managed by the run loop. And then there's a higher level construct called operations, which basically lets you, instead of thinking of your implementation as, I want this thing to happen on this thread, you can think of it more as, I've got this thing that has to happen, and I want it to happen at some point, and it depends on this other thing that has to happen at some point. And you can basically set up a dependency graph of operations that have to occur at some period of time in some particular order with their dependence. It's a graph. And you can specify priorities so that certain things are more likely to happen first. And basically, you can hand these things off to the system, and it'll schedule them on its own threads as time becomes available, and maintain your dependencies that you've set up, and basically run these units of work for you. So you kind of encapsulate your work as units and let the system handle scheduling them. So the demo I was going to show you was using NS operations to speed up the thing we talked about with table views, where when you scroll something in, it blocks waiting for the data. It's actually not going to be part of the assignment until next week, so we'll talk about this on Tuesday instead. So you guys are going to be using table views for the assignment this week, so just a quick example of what this is going to look like, right? It's basically the object reuse we just talked about. In your table view cell for row at index path method, the first thing you do is call get a cell, so table view DQ reusable cell with identifier. If you didn't get one, so cell's still nil, then you can allocate a new one and auto-release it, because the thing you got back from DQ reusable cell with identifier was auto-released. So you want to make sure that when you return these things, in this case we were going to return an auto-released object. In this case, +1 retain count also want to return an auto-released object. And then you do your configuration at the cell down here. So in either case, you've either DQ'd a reusable one or allocated a new one. Then you just run the same code path from there on out to fill it out with images and text and whatever you want, and then return the object. Sorry, I kind of ran out of time there. So those are the important points. I think we kind of skipped pretty quick at the end, but we'll get back to a little of the operation stuff. So that's pretty much it. You know, performance, it's as much an art as it is a science. You kind of get a feel for where these things are going wrong over time after you've seen them a couple times. A little bit of it's intuition, and a lot of it's also, you know, using the tools right and finding the places where these things are really happening. So don't waste your memory. Thanks.
For more, please visit us at stanford.edu.